Hi, my name is Carly Sylvan. I'm an AP Chemistry student, and I'm going to be explaining topic 7.9, Introduction to Le Chatelier's Principle, and 7.10, Reaction Quotient and Le Chatelier's Principle. So first off, what's the purpose of learning about this? Well, here's the question. If a reaction has reached equilibrium, so that the concentrations are now constant, what will happen if the conditions are changed? Le Chatelier's principle is really useful because it allows us to predict what will happen to a system when it responds to stress or changes that are applied to it after it reaches equilibrium. So here's the definition. If a dynamic equilibrium is disturbed by a change in conditions, the position of equilibrium moves to counteract the change. The changes that we're going to be looking at are changes in concentration, temperature, and volume. So first let's look at concentration. Suppose we have the following reaction. This is the synthesis of ammonia, and it's at equilibrium. And let's say that more nitrogen gas was added. What will be the outcome? Well, Le Chatelier's principle says that the system will move to counteract the change. So if nitrogen gas was added, the system will shift to the right, towards the products. And since the equilibrium position is shifting towards the products, the concentration of ammonia will have increased and the concentration of hydrogen gas will have decreased. And here's a helpful visual to show how this all works. So the system was already at equilibrium, and then here is when the nitrogen gas was added. The concentration of the product ammonia increased and the concentration of the reactant hydrogen gas decreased. And finally, equilibrium was achieved again. Now let's look at another type of change, changes in temperature. So when dealing with changes in temperature, it's really helpful to think of heat as a product or reactant, depending on whether the reaction is endo or exothermic. So to review, if a reaction is endothermic, it is indicated by a positive delta H, and the forward reaction absorbs heat, meaning heat is a reactant. If the reaction is exothermic, delta H is negative, the forward reaction releases heat, so heat is a product of the reaction. Here's an example. The delta H for this reaction is negative, and the change that occurs is the temperature of the surroundings being decreased. The first thing that we should do here is write in heat as a product or reactant. The reaction is exothermic, so heat is a product. So the heat will go here. And next we're going to figure out what will happen because of this temperature change. So if the temperature is decreased, the system will counteract the change by producing more heat and shifting towards the products. Finally, we're going to look at how Le Chatelier's principle applies to changes in volume. The ideal gas law is key to understanding these changes. So to review, the ideal gas law says that PV equals nRT. From this law, we know two things that are going to help us here. First, that pressure and volume are inversely proportional to each other. And the second thing is that pressure and N, the number of moles, are directly proportional to each other. So here's a sample reaction. The first thing that we should note is the difference in the number of moles of gas on each side. So we have 3 on this side and only 2 on this side. If the volume of the container is decreased, the pressure will increase because, like we said, those two are inversely proportional. To counteract the change, we need some way to decrease the pressure so that this will counteract this. And so the way we do this is by shifting the equilibrium position to the right, towards the products. And when we shift it towards the products, we're going to be producing fewer moles of gas because the products only have 2 moles versus 3 moles. So when we shift right, we're going to be decreasing N, which is the moles of gas. And when we decrease N, we're also going to decrease P because those two are directly proportional. Here's a summary of how a system will react to changes in volume. So the volume decreases, the pressure will increase, and the equilibrium position will shift towards the side of the equation with fewer moles of gas. And the opposite is also true. Here's a nice diagram from the textbook that shows how this can go both ways. So for this reaction, when volume is decreased, there's a shift towards the products, And when volume is increased, the pressure is decreased, and to counteract that, the new equilibrium favors the reactants to produce more moles of gas. Now that we know how the system will respond to each of these changes, we can apply this to predict the effect that it will have on measurable properties such as pH, temperature, and color. So now we're going to look at how Le Chatelier's principle can be used to predict the effect that a stress will have in pH. So here's the equation for the dissociation of acetic acid. The change that we're looking at here is if we were to add more of the acetate ion. Due to Le Chatelier's principle, this would cause the equilibrium to shift towards the reactants. And this will in turn cause the concentration of H+ ions to decrease. And this will cause a change that we can measure, which is an increase in pH. Now we're going to look at how we can predict changes in temperature. So let's go back to this example here from before, an exothermic reaction. And again, we're going to write in heat as a product. But this time, instead of changing the temperature, we're going to change the concentration of one of the compounds and observe the temperature. So the change is going to be an increase in oxygen gas, which causes the equilibrium to shift towards the products. And when the equilibrium shifts towards the products, since heat is a product, there will be more heat produced, and this will lead to an increase in temperature. Finally, let's look at how Le Chatelier's principle can be used to predict changes in color. In this case, there are two differently colored cobalt compounds on each side. We have pink on the left, and then we have blue on the right. And the other two compounds in this reaction, aqueous chloride ions and water, are colorless, so they won't affect it. Let's first add heat to the right, since delta H is positive. Now let's think about what would happen with the two temperature changes. So initially, at equilibrium, there are approximately equal amounts of the blue and pink compounds, so it would look something like this. And if the temperature were to be increased, there will be a shift away from the heat towards the product side. So it would shift this way, and more of the blue ions would be produced. So the solution would look something like this. And if the temperature were to be decreased, more of the pink ions will be produced because it's shifting towards the heat this way. And the solution will look something like that. Now that we have an idea of how Le Chatelier's principle works, we're going to look at how it can be explained by the relationship between the reaction quotient Q and the equilibrium constant K. So first, let's review what these are. So Q tells us the relative amounts of products and reactants present during a reaction at a particular point in time, whereas K tells us the relative amounts of products and reactants present at equilibrium. In short, Q is where the reaction is, and K is where the reaction is going. And when these two are equal to each other, the system is at equilibrium. So, how does this apply to Le Chatelier's principle? Well, the changes that we're talking about before, changes in concentration, temperature, and volume, these cause Q to differ from K, thereby taking the system out of equilibrium. The system responds by bringing Q back into agreement with K, thereby establishing a new equilibrium state. And this here, bringing Q back into agreement with K, this is the same as counteracting the change in the definition of Le Chatelier's principle. So looking at changes in concentration, let's go back to this example. We figured out that the expected outcome based on the change would be a shift towards the products because we're increasing the nitrogen gas, so it would shift this way. But let's look how this can be justified using Q and K. So to do this, we're going to use this diagram here. And on the x-axis, we have increasing values of Q and K, and the dashed lines represent different periods of time. So initially, before the change, K and Q are equal to each other. And when nitrogen gas is added, there are more reactants, and so Q decreases, but K stays the same. And to make Q and K equal again, the reaction shifts towards the products, and then we have the new equilibrium. So what about a change in temperature? So this is the example that we used before. We're going to write in heat like we did in before. It's exothermic, so the heat goes here. And we're going to use this diagram again. So we said that the change is the temperature being decreased, and the outcome is a shift towards the products. So initially, K and Q are equal. And then when the temperature is decreased, the equilibrium shifts towards the products, towards the heat, which will result in a higher K value. So K increases and Q stays the same. And finally, Q shifts to the right towards K so that they are equal to each other. Here's a quick summary of Q and K. When they're equal, it's at equilibrium. When K is greater than Q, the reaction will shift to the right towards the products, and when K is less than Q, the reaction will shift towards the left to the reactants. And that's it. Here are the sources that I used to make this video. Hopefully you now have an understanding of Le Chatelier's principle. Thank you for watching.